Hello, Andrew Logan here with an overview of my paper on the characteristics of the zeros of the Riemann zeta function. I'll give you a link at the end of the video to the paper and also my contact details, so that if you do have any questions or comments, please do get in touch. What we'll be doing with the paper is investigating the characteristics of the zeros of the real component of the Riemann zeta function of S by using the zeros of the real component of the Dirichlet eta function, which has the same zeros as the zeta function. Remembering that a necessary condition for a zero of the complete zeta or eta function is a zero of the real component. We'll be showing that the derivative of the real component for a fixed imaginary part of S is always positive for negative or zero values of the real component of the function, meaning that each value of the imaginary part of S produces at most one zero. If we combine that with the fact that the zeros of the Riemann z function are also the zeros of the zeta function, and z of s equals z of 1 minus s, this leads to the conclusion that the Riemann hypothesis is true. Getting into the meat of the paper, starting with the zeta function, 1 over n to the power s, the Riemann's original definition, of course only convergent for the real part of s is greater than 1. Riemann obviously extends the zeta function analytically for all s in his paper and defines the z function, which has the same zeros as the zeta function, and shows that it can be written as a power series. All this is available in Edwards. Looking at that in a little more detail and emphasising, using s equals a half plus it and defining t equals a plus bi, that means that s minus a half equals it equals ai minus b, and you end up with this power function. The implication of this is that if half plus b plus ai is a root of the function, then so is a half plus b minus ai, but also so is a half minus b plus ai and a half minus b minus ai, all roots of z of s and therefore all roots of zeta of s. For the rest of the paper, the real part of s, half plus or minus b, will be referred to as sigma. What we will do first is have a look at the characteristics of the real and imaginary components of the zeta function. We can do this quite easily because there are a number of numerical applications which can be used to calculate the various values of the real and imaginary parts of zeta. Now, looking at this, which have been generated using the numerical application in MATLAB, the dashed lines are the real part of zeta of sigma plus ai. The dotted lines are the imaginary component of sigma plus ai, with the colours representing different real values of sigma, and the imaginary part of sigma being along the horizontal axis there. And we can start to, if we look carefully, you can start to see a function, an implicit function if you like, of real part of zeta equals the imaginary part of zeta, and we can trace what that function looks like. So looking at that in a bit more detail around a known zero of zeta, around 14.1, then we can see here that as the real part of zeta, real part of s gets smaller, then the function real of zeta equals imaginary of zeta has a very steep curve. It's actually with a very strongly positive curve, because this is going down as the real part of s gets smaller. Quite important to keep that in mind. The next thing we need to do is to have a look more formally at how we can show that there is always a positive derivative for the point where the real part of the real component is equal to 0. Excuse me. In the following part of the paper, we shall only be looking at the values of b between plus a half to minus half, or in fact, sigma greater than 0 and less than 1. We do know already that the zeros of the zeta function, therefore the eta function, are only in the critical strip between plus half and minus half, or sigma greater than 0 and less than 1. So we're focusing our investigations on that critical strip for this paper. The first step is to have a look at the Dirichlet eta function, also known as the alternating zeta function. It's related to the zeta function by this expression here. It is convergent, not absolutely, but it is convergent uniformly for sigma greater than 0. Now, because of that, we have an expression we can use to explore the characteristics of the real component, imaginary component, and or function zeros of the zeta function in the critical strip. Once again, it's important to emphasize that the eta function has the same zeros as the zeta function, and that as zero of the eta function requires coincident zeros of both real and imaginary components of the function. Because of that, we can just look at the zeros of the real component to establish possible locations for zeros of the entire function. Now, if we have a look at the definition of the eta function, 1 minus 1 over 2 to the s plus 1 over 3 to the s, etc., and extracting the real part for one term, cos a log n minus I sine a log n over n to the sigma, on the basis that a is the imaginary part and sigma is the real part of s, we can extend that into the series representation of the real part 1 minus cos a log 2 over 2 to the sigma plus cos a log 3 over 3 to the sigma, etc. Expression 1. For the next part of the series, for the next part of the paper, we'll be looking purely at the series representation of the real component of eta of s, but with a fixed imaginary component of s. This is because we are looking for, what we're trying to do is to establish if there are, how many zeros there can be for the same imaginary component of s. If b does not equal 0, then that will mean there will need to be at least 2 zeros for one value of a. So, starting with and writing the fixed value of little a as big A, then we can differentiate with respect to a single variable, so differentiate expression 1 with respect to sigma only, and this results in the derivative equals log 2 cos a log 2 over 2 to the sigma minus log 3 cos a log 3 over 3 to the sigma plus log 4 cos a log 4 over 4 to the sigma, 4 to the sigma, etc. Now, this expression is also convergent for sigma greater than 0. Two reasons. Partly because the eta function is uniformly convergent, but you can also look at it in its own right. You can see it because log n over n to the sigma, now for any positive value of sigma, that eventually becomes a monotonically reducing series tending to 0, which means that after a potentially large number of initial terms, you end up with a convergent series when you look at it with the Dirichlet test. Now, for the next part, I will just look at a partial sum. It's easier for calculation, but you'll see that it does not affect the overall result. So, looking at expression 1 equals 0 for a fixed a, and for the sake of convenience using n equals 4, we end up with this expression here, which implies that cos a log 2 over 2 to the sigma minus cos a log 3 over 3 to the sigma plus cos a log 4 to the 4 to the sigma equals 1, which also means that if we start looking at the individual terms of the derivative, we can express those in terms of pure logs and expressions involving the cos a log n over 3 to the n, or n to the sigma terms as well. If you add all of those together, they end up with the fact that the derivative equals this expression here, expression 3. We can also use a different approach to the derivative as well, and so we end up with different representations of the derivative in terms of logs and the cos a log n over n to the sigma terms as well. Summing all those terms together, you end up with this expression, and using that same process you can see that you will end up in the general case with n to whatever value with this expression here. The important thing about this expression here, obviously the right hand side of this expression does not converge because you've got all of the log terms here, so when n tends to the limit you've got an infinitely large sum there. However, it does work for n up to any value that you choose. Looking at that in more detail, the magnitude of this component is the same potentially as the magnitude of this component. So this, ignoring the cos a log n to n over n to the sigma terms for the moment, magnitude of this is the same as the magnitude of this. However, once we consider this term, as soon as sigma is greater than 0, then the magnitude of this term is always less than 1, which means that the magnitude of this, the magnitude of this part will always be less than the magnitude of this part. Given that this part is always positive, it means that the derivative will always be positive for expression 1 equals 0. Very important. Since the derivative is always positive when the function value is 0, that means that when the function crosses the axis, it's always with a positive derivative, which means there can be only one 0. If there were more than one 0, you'd have to have a negative derivative or possibly a 0 derivative, but you can't have that. Very important. The other thing to look at is that even though this expression does not converge, it is valid for all n, which means two things. One, that if you look at the partial sum approach, then for whatever value of sigma you use and whatever value of a you use, you will be able to estimate the value of the derivative to whatever accuracy you like, and it will always be positive. The other thing you could argue, of course, is that the derivative will be positive even when n is at the limit, because there is no way that you can get to a negative value of the derivative with that expression, even if the expression does not converge. Now, if you combining that with the fact that combining the fact that you can only have a single 0 with the fact that z of s equals z of 1 minus s, that means that the real value of s can only be a half if there's going to be a 0, which is the Riemann hypothesis. Just reviewing the conclusions I've got here, just reviewing what we've just done. If you remember, in section 2.1 we looked at the paths of the points where the real part of zeta equals the imaginary part of zeta, showing, and we saw that it was unlikely that you'd have two zeros of zeta s for the same value of the imaginary part of s. Section 2.2, we introduced the Dirichlet function, mentioning that it's the same zeros as the zeta function. We developed the series representation of the real part of the eta function. We looked at the series representation of the derivative of the real part of the eta function for a fixed a value. We saw that derivative was always positive when the function itself is 0, actually in fact 0 or negative for a fixed value of a. Once we'd shown that, then we can conclude that the real component of the eta function has only a single 0 for a fixed value of a, the imaginary part of s, which directly leads to the fact that if there's only a single 0, it has to be at the real part of sigma equals a half, which means that the Riemann hypothesis is true. As promised, here's the link to the paper, and here's my email address if you'd like to get in touch. Thank you very much for listening.